That's the way I just hold it.
Got this. There we go.
Let's go.
I'd like to thank everyone for coming today. This is our annual East Tennessee section of the American Chemical Society Lind Lecture. I am the chair of the East Tennessee section of ACS. My name is Heather Boyd. I'd like to recognize a few of our other our executive club members that are here today. All right, we have our past chair, Stephen Neal. We have Al Hazari, who is one of our counselors. Our other counselor, we have John Larice. All right, we have Brian Long, who's our member at large. And I believe that is everyone that is here today. All right, what I'd like to do now is I'd like to hand over the mic to Dr. Al Hazari. He's going to give a few words about the Lind Lecture, and then we'll hear from Mike Kilby. Who's going to introduce?
Again, welcome to everyone. This is a special time of the year when we gather and celebrate the SESC Lind Lecture series. And I hope you got a copy of the brochure, the handout here, and it tells you everything about the lecture series, which started in 1948. I wasn't born, so I don't know. It's a long time ago. All right, you're supposed to laugh, yes. Thank you. But the idea is that this lecture series started way back then, and in 1953 it became, it has a new name, the Lind Lecture. And we, over the years, many distinguished scientists, chemists, researchers have come and stood here and presented the lecture. And you can see the list of all the folks who have come, and some of them went on to get Nobel Prizes. So we are really excited about this year's speaker. And he's from Austin, Texas, by the way. That's where my daughter lives. And as I said, the life of Dr. Samuel Colville Lind is in the brochure again here. So take some time to look at this list of distinguished, as I said, scientists, researchers, chemists who have been part of this lecture series. It's exciting to see everybody and the lecturer, of course. Thank you. And I would like to ask him to come to the front here for a second. Make a presentation. First, we'd like to present you with a plaque that says Dr. Grant Willson, 2017 SC Lind Lecturer, East Tennessee Section of the American Chemical Society.
Thank you very much.
Okay. Want to hold it up so that our photographer takes the picture? Let's hold it this way. You want to take another picture? How's our hair? All right, good. Just as a token of appreciation, wait, don't go away. We'd like to present you with an envelope, and make sure you keep this in a safe place, and look at it later. It's a generous envelope that we'd like to present you, and as a token of our appreciation, you coming down here. You want to take a picture of the envelope? Well, we'll talk about that later. All right. Since we want to move on, and you can stay here. That's okay. Yes, that's okay. Dr. Kilby, come forward and let us hear a little more about our speaker. Dr. Kilby, right here.
Thank you, Al. First of all, how's the sound in the back? Evan, is the sound good? Okay, thank you. Okay. I got a thumbs up and a thumbs down. I'm not sure. Thumbs up. Okay, thank you very much. It's my pleasure to introduce Professor Grant Willson from the University of Texas at Austin as our 2017 Lind Lecturer. Professor Willson received his bachelor's degrees and his PhD degree from the University of California at Berkeley, and his MS degree from the University of California, Santa Barbara. He is a professor of chemistry and chemical engineering, and he's also the Rashid Regents Chair of Engineering at UT Austin. He is well known and recognized internationally for his work on materials and processes related to the microelectronics industry, where issues of materials design, feature size, scalability, resolution, all derive from the properties of the materials. He has won numerous awards, and since this is the East Tennessee section ACS lecture, I will mention a few of them. He's a fellow of the American Chemical Society. He is a senior editor of an ACS, a prominent ACS journal, ACS Nano. He has won several awards from the American Chemical Society. They're enlisted in your bulletin, and I won't take time to read them all. He's the co-inventor or inventor on more than 40 issued patents, more than 400 papers, and the last number I had for PhD students was more than 75 PhD graduates. And he's quite young. He joined the University of Tennessee, Austin in 1993. Prior to that, he was at IBM Almaden Research University. Thank you, Al. UT Austin, University of Texas at Austin. Prior to that, he was at IBM Almaden. He has won numerous high-level awards, and I will only mention a few of them. In 1992, he was named as a member of the National Academy of Engineering for the development and advances of new photoresist materials for the microelectronics industry. He was honored as an ACS Hero in Chemistry for similar work in that area. He received the Aristotle Award, which is given by the Semiconductor Research Corporation, and that award is given for deep commitment to teaching and education and mentoring of students. He is certainly accomplished in that regard. In 2009, he received the Gordon Moore Medal, which is named for the co-founder and chairman of Intel Corporation. In 2007, he received our nation's highest award for technology. He received the National Medal of Technology and Innovation, and that was for the creation of novel lithographic imaging materials that enable the manufacturing of smaller, faster, and more efficient microelectronic components. In 2013, he shared the Japan Prize, which is the nation's highest award for technological innovation, for the development of chemically amplified resist polymer materials and innovation in semiconductor material properties. I ask that you please join me in welcoming Professor Grant Willson to the University of Tennessee.
Does it work for me? Hello, hello? Yes. Okay, wow, we're going to do this. It's a pleasure to be here. It's my first visit to UT, well, at least this UT. And it feels very familiar. You guys have a nice school color. It's similar but not identical to ours. And here you see this pretty picture of our campus that features the sort of architectural icon of the university, which is this tower that's essentially visible from almost everywhere in Austin. And in the evening, if there's been something important happen, they signal that by illuminating the tower with these orange lights. And so if we win a football game, for example, the top only of the tower is illuminated in orange, the rest is white. If they win something more important like a league championship, then the whole thing may become orange. And on very rare occasions, they ask the people who have offices in here to leave their lights on in some pattern. And in this case, this was taken the year that we won the National Football Championship, which was a long time ago. And when I say that there are some commonalities between the university besides the UT and the orange and so forth, we both have really scary problems in football. And I'm not sure exactly what we're going to do about it. We just spent $21 million trying to fix it. And I'll let you know, so far we're 50-50, even Steven. But it's a beautiful campus. I'm pleased and proud to be there. And the chemistry building is in this general part of the campus, and the chemical engineering building is just out of the picture over here. We have this famous logo, or our mascot, whose name is Bevo. There are 15 of them now. This guy, I'm sorry to say, passed away, and now we have a baby bevo with very short horns, and he's growing fast. And his strange horns are captured, of course, in the logo, and he's known, obviously, as a longhorn steer for obvious reasons. And so people who go to the university call themselves longhorns, and they behave strangely at times by, for example, holding their hands in this shape, which is somehow meant to capture the shape of that thing, and yelling at each other, "Hook 'em horns," which is, you have to admit, if you didn't go there, it's a very, very strange thing. But everybody who goes to Texas, or has been in Texas, knows this. And I mean, there are residues of them here. Hook 'em. Very proud to see them here. As I say, we're national champions. It's been a long time ago. You see, very interesting. You never know who you're going to see do this. I mean, some of them are terrible people. Some of them are very nice. I like that one. I don't know about this one. That guy does it with his left hand. I think probably he has tracks on his other arm or something. But this one, I'm not sure even knows what he's doing. And this one comes to every football game and screams and shouts. He's a tremendous fan of the University of Texas football team. This one, that child's father swore that he did not put her hand in that. She's not the youngest person I've seen do it. This is the youngest person. Definitely this child was born in Texas. Some people don't have the dexterity. But when they finally can do it, he's got it backwards. But he's learning, as you can see. And you never know who you're going to see do it. This is my current research group. They're positioned outside the building where our laboratory is and in front of a thing that I guess is a new landmark of the university. That's a $1.4 million sculpture that is recently installed. It's really quite lovely, and very proud of these young people. They're my longhorns, so to speak. So this is a Texan, but he's not a longhorn. He didn't go to the University of Texas. He is the person who invented the integrated circuit and received the Nobel Prize in 2000 for that invention. And here you see him holding the circuit, and here's a close-up of it. Its size is about the size of the end of his thumb, approximately. He worked at Texas Instruments in Dallas, and very famous and very important discovery that he made. His circuit had one transistor and a couple of other components, but it had only one transistor. And then shortly after this, people from Bell Labs and others put together a company called Fairchild Semiconductor in San Jose, California, and they began to try and produce these things as planar circuits. And one of those people was Gordon Moore. He and the group from Bell Laboratories started that company, and Gordon Moore published a paper many years ago in which he noted that if he looked at the number of transistors being produced against time, and like engineers do, tried to find a way to linearize the relationship, that he could do so by plotting it as a semi-log function at log base 2. And he did what engineers do. He extrapolated those few points to infinity and predicted what would happen in the future. And so this became something called Moore's Law, and it's the thing that drives the semiconductor industry. It drives it because you have to stay on this line, and if you fall into this part of the graph, you go away. You go out of business, basically. So it's not a law like Fick's law or F equals ma or E equals mc squared. It's a financial truth. The truth is, if you can't stay on that line, you will go away. And so, unfortunately, many famous people have not been able to stay on the line, and they have all and this part is making these kinds of devices, have gone out of business. On the other hand, if you can stay in this part of the graph, you reap rewards that are good for you and good for your employees and make all persons associated with the activity happy. So one must stay in the blue area, or if possible get up into this even better region. Today this thing has gone from 1 transistor to 1.4 billion transistors on a piece of silicon about the same size as the one you saw in Kilby's hand. That's a significant increase. And there are so many transistors on this little piece that one of them, if you divide the cost of this by the number of transistors, one of them costs less than a printed character like the letter A in your local newspaper. Hard to believe, but true. Transistors cheaper than a letter A or a period. The reason it's able to get that many on there is simply because they're so unbelievably small. The smallest structures on that device are smaller than the dimensions of a virus. Yet all of those wires so small and the transistors so small and the connections so small all work. It's a tribute to the ingenuity of man that it's even possible to make one such thing, let alone to make hundreds of thousands of them an hour and have them all work. It's really remarkable business and fun to be involved with. So they're making things about 22 nanometers or 20 nanometers. This is a scanning electron micrograph of an influenza virus. These are the viruses, or the viri, or whatever they are. And this is Willson's attempt to draw to the same scale a 20 nanometer line. So you can see they're incredibly small structure. And our job is to make them smaller still by some method. And so here you see my group busily working, and here's Gordon Moore watching over them, because not only must they make them smaller, but they must make them smaller at a pace that keeps them out of the region where that angel of death resided on the plot. So we have to go fast. The way this printing process is done is by something called photolithography, which an original drawing of one of the circuit levels of the circuit is made very slowly at high cost using focused electron beams. And without going through the details of how it's done, let me tell you that it's very slow. It takes about 24 hours to produce one such level. There are 30 or 40 such levels required to make a functioning device these days. And this thing is inspected to make sure that it's absolutely perfect and there are no flaws in it. And then this image is projected through a lens system onto the wafer in much the same way as that projector is projecting the image onto the screen. And the material that is on the substrate is photosensitive, and it undergoes a chemical reaction upon exposure to light that renders the exposed areas either more soluble or less soluble in some solvent, such that you can pattern it and get access to the substrate. This is a lens that reduces the size of this structure by a factor of 4 when it's printed on the wafer. And it's a cartoon that actually demonstrates this lens. This lens is as big a lens as people have ever learned to make. The glass required to make it costs about $3 million before they even start to grind it. And it weighs far more than an automobile. It's incredibly sensitive. Small changes in hundredths of a degree of temperature put it out of focus. Barometric pressure changes of a few millibar are enough to put it out of focus. And it can never be allowed to lay flat on its side. It's made in either in Japan or in Europe, and if it's going to be shipped out of that, where it's manufactured, it has to be shipped in a special airplane that can hold it in its vertical. This thing, by the time it's finished, costs in the order of $60 to $90 million for one such projector. And you have to, they can produce about 100 or 150 wafers per hour And they have to, depending on how you calculate your business, you can recognize that you need to make a lot of wafers in order to pay off the mortgage on these tools. Anyway, unfortunately, things are coming to an end here. The resolution of such a system based on a lens projection is equal to some constant, actually the Rayleigh constant, so-called, times the wavelength of the light that's being projected divided by the index refraction of the medium with the highest refractive index that's in that optical stack, and the sine of the capture angle of the lens. So basically what you want is the biggest lens you can get, possibly, that you can possibly make, and you want some high index material in this system and the shortest wavelength. So we've worked on these parameters and these parameters for decades. I've been involved in it for longer than since what year did he say he was born? And what's happened now as a result of all these people all over the world working on all these things is that we're using water for this, and there'll never be anything else. I can tell you, if you ask me later, I'll tell you why that's true. This value cannot be smaller than 0.25, and they're running at 0.3. The wavelength is 193 nanometers, which is shorter than you can generally do on a laboratory spectrophotometer. We tried 157, it won't work, so that's the shortest wavelength that there'll ever be. The sine of this angle is 0.9, and I'm not going to ask you how big it can be. And that gives a resolution of 45 nanometers. You saw that the Intel was producing 20-some nanometers, half of that. So you ask yourself, what's happening here? Is this the end of Moore's law? We can't have it be the end of Moore's law. It's not allowed. We can't allow that to happen, because if it did, there would be total worldwide economic collapse. There would be famine, nuclear holocaust, insurrection, and a variety of other terrible things would happen if Moore's law came to an end. So what do we do now? I don't think they know what to do. I'm very sure she doesn't. Hopefully he may, I don't know. That one doesn't want to talk about it. He's involved in trying to deal with North Korea. This one, you know who that guy is, Brantley? He just moved here, right? Brian, who is that guy? Somebody, who is he? That's your senator, right? Maybe he knows. It's possible that he has the solution, but I'm not certain. At any rate, someone's got to find a solution. Right now what they're doing is, since they can't print things this close together, what they do is they print once this kind of pitch, and then they come back and print again, which means that several things, and we won't go into the details of, but even with PowerPoint, it's a bit difficult to juxtapose those things exactly. And you can imagine if they're the size, half the size or less of a virus, how easy it might be to get them positioned. Plus, it takes 2 such machines now per wafer, if you will, or they're printing at half the speed. Twice as many people, twice as many machines, twice as much floor space, twice as much electricity. It's expensive, but it works, and that's how Intel is making those structures that you see. Not the ideal solution. So we need some kind of a miracle to fix this problem, because we can't have the Holocaust and so forth. So I don't have any miracles to report to you, but I can show you some things that we're doing to try to help solve the problem, and try and inspire you, I hope, to help us solve the problem. First, I'm going to tell you about solving the problem by unzipping. I was going to tell a joke about that, but this is Webcast, and I won't. So first, let me explain how these imaging materials work. This is the old-fashioned version that made the first many, many billions of dollars. Okay? It's made by dissolving a mixture of this resin, it's Novolac resin, phenol formaldehyde type resin, in organic solvent. And then adding to it this monomeric species, which is called a diazonaphthoquinone. It doesn't matter what it's called. It's a lipophilic substance. And this is soluble in organic solvents. It's also soluble in aqueous base by virtue of the acidity of this phenolic hydroxyl group. And so what I can do is to cast a film of this material and then immerse the film in a solution of aqueous base. If I just cast the film of this, it dissolves at a very high rate because it's an acid. And so here on this axis you see the log of the dissolution rate. So it dissolves very, very fast, the pure Novolac. If I compound it with this diazoquinone, it slows it down because it's like mixing sugar and butter or something like that, right? It slows this dissolution rate down until finally you can slow it down to the point for all practical purposes in 60 seconds or so, it doesn't dissolve at all. And now if you shine light on this film, this substance is converted by a series of well-known reactions to first it forms a ketene through the so-called Wolff rearrangement, and then the ketene adds water to form a carboxylic acid. So I've switched this lipophilic material to a very hydrophilic, even acidic material, and therefore the film dissolves again very, very rapidly. So I take a material that's insoluble in base, shine light on it, selectively convert a region of it into an area that dissolves quickly, then immerse the film in base. This part dissolves out, this is left behind, and I can now transfer this pattern into the substrate and either etch away material or deposit material or whatsoever, and use that to build up the layers of semiconductor, conductor, insulator that are used to produce the device. Okay? Unfortunately, as we progress to shorter and shorter, smaller and smaller structures, we're doing the exposure at the so-called eye line of the high pressure mercury lamp, 365 nanometers, and everything was working fine. And this is the absorbance spectrum, which doesn't show well on this projector, of the Novolac resin. See, it's transparent up here, but it absorbs light to the left of that, the shorter wavelength. So in order to make higher resolution, I need to move this over here. And you can immediately see there's a serious problem. That resin, which is transparent over here, looks like aluminum foil at that shorter wavelength. It's absolutely opaque. So no light can reach the lower reaches of the film to do the chemistry necessary for patterning. So that chemistry is not going to work. Need a new material. So this is a description of the new material that emerged to solve that problem. It's based on polystyrene. This is polystyrene. It's polyparahydroxystyrene protected with a tertiary butyl oxycarbonyl group, which is a common protecting group for peptide chemistry, for example. This group is labile to thermolysis. If you heat the material, this bond breaks. It forms isobutene and carbon dioxide and loses about half of its mass. So here I have an experiment, a thermogravimetric analysis in which we're heating a sample of this polymer. And it does nothing, it does nothing. It reaches a threshold temperature around 200 degrees, 190, and it loses half of its mass. And now I'm heating this material here. So I've converted this into this. And this is like car wax. It's lipophilic, hydrophobic, greasy stuff. And this is polar, even acidic substance. So I've switched the solubility tremendously by this thermolysis reaction. The thermolysis reaction turns out to be acid catalyzed. So if I mix a small amount of acid with the sample before I heat it, the same reaction occurs, it just occurs at a much lower temperature, which is, it reduced the activation energy for the reaction, which is the classical example of catalysis. It's not consumed in the reaction, it just reduces the activation energy. So what we do is to put a neutral species, this salt or one like it, into the mix, this and this into a flask, pour solvent on them to make this solution, and then cast a film of that. And now if I shine light on this, it forms acid. That happens to be the strongest acid known to man, but you don't have to make that strong of an acid, but you make an acid. And then if you bake the system to a temperature between these two, only where the light struck the film and the acid has been generated do we have this reaction occur. I haven't reached the threshold temperature in the areas where no light struck the film, therefore nothing happens. So now I have an area that's this polymer and an area that's this polymer. If I stick it into base, this dissolves and leaves this behind. If I stick it into hydrophilic solvent like toluene or something, I can dissolve this away and leave the polar polymer behind. So I can, either way, I can image the material. We okay? You're sure? There will be a test at the end. And you can interrupt me at any time, please. Thank you. Yes?
Curious, shine light on a thiol, sulfur containing.
It's a sulfonium salt. So it's this is this hexafluoroantimonate anion, and it's the sulfonium salt. So it's actually inorganic. It's like an inorganic salt.
Well, being an inorganic chemist, it's interesting to see the sulfur and all the phenols disappear and H plus replace them.
Well, the equation is not all that well balanced. That's going to be one of the test questions. There are other products formed, but they are neutral and not involved in the reaction, but I confess I didn't balance the equation. Brian can do it after the lecture. So, now, that's all a preamble to explaining to you what the problem is. So, what happens is you shine light and you make a latent image of acid in the film. The little dots are the acid, okay? And then you bake it and let the acid do its thing. And what happens is the acid doesn't understand that it's only supposed to stay in the area where the light struck the film. So classical mass transport, sort of non-classical mass transport occurs, and the acid diffuses sideways such that when you develop the film, the image that you produce is bigger than the image on the mask. When we first started doing this, this delta was on the order of 20 nanometers or so, right? So we could fix the problem by just making this 20 nanometers narrower and windage, quote unquote, windage the pattern. Today we're making 20 nanometer images, which means that the opening would have to have negative width in order for this to work. And so that's not good. And this is bad, very, very bad. So here you can see one PhD's worth of effort to simulate this. It's a fascinating reactive transport process, which in this picture, the region that's to the left of this blue line has acid in it. This is the latent image of acid. And at time equals 0, the thing is raised to the temperature at which the reaction takes place. And the acid starts transporting itself into the unreacted polymer film, moving sideways. And of course, it's a stochastic process. So how far the edge of it is poorly defined, meaning that the edge is not straight, it's rough. That's bad. Where is the edge? Well, I don't know. Is it here? Is it here? Is it here? You can't really decide where is the edge. That's bad. Second thing is that there's this bias that the image is larger than it should be. And there's some interesting other questions. For example, why does it stop? The simulation didn't stop. The diffusion stopped. And why is that true? There are people here who are very interested in that. Professor Stein and others are actively studying this. We worked hard on this. It ate up 2.5 graduate students, and I think we finally sort of understand it, but it's certainly important, and it's good luck that it stops. Otherwise, the whole wafer would become soluble. So we need to fix this in some way. It's causing terrible problems. In the next kind of lithography they want to do, the roughness of the sidewall created by the stochastic diffusion phenomenon has to be down in this region. And they need to be able to expose it at a low dose down in this region and in order to achieve their production goals. And you see here's data from a company who has access to every single sample that anybody makes because everybody wants to sell it to them. So they're happy to give it to them. And they test it. And what you see is that there's an exclusion zone down here. You can go anywhere you want except where you want to go because of some serious problem. So that phenomenon has been termed the triangle of death. So unfortunately, we're in the triangle of death. Let me explain the triangle of death for you. The triangle of death has three sides: sensitivity, which is how much light is required to pattern the film; resolution or blur, that is what's the smallest structure and what is the fuzziness of the structure; and then the line edge roughness on this axis. And the way this works is that you're allowed to change any one of these sides, the length of any of these sides. I can improve the resolution by making this smaller, but the area of the triangle must remain constant. So what happens is if you can gain on one of these variables, but you lose on one of the others, at least one of the others. So you can't win. It's like having a balloon, right? And you want to make the balloon smaller, so you squish it, and unfortunately it pooches out someplace else because its volume is constant. In this case, its area is constant. So the principle is clear. It's hard to win without being able to get out of the triangle. So how can you get out of the triangle? The bad actor here is the catalyst, because it's the catalyst that is diffusing. And so we have to find a way of escaping not using the catalyst. But the catalyst is the key characteristic of the system that provides gain. That is, you produce one hydrogen atom or one mole of acid, or however you want to define it, and that acid catalyzes the breaking of many, many, many bonds, which means that it doesn't take much light to print the thing, which means that you can produce a lot of them per unit time. So we need this high speed or high sensitivity to light that derives from the gain in the system. And we need to achieve the gain without using a catalyst, because it's the catalyst that's diffusing and causing the problem. So we sat around for a long time trying to figure out how to do that, and came up with an idea, a couple of ideas, only one of which we've tested because I couldn't figure out how to do the other one. We're using these so-called unzipping or low sealing temperature polymers, and I'll show you more about that in a second. The design provides means of breaking many, many bonds with a single photon, which is what provides the gain. And it does not involve a catalyst, and it's limited, the reaction is limited to a single polymer chain. It can't hop from one chain to another to another. All of the chemistry that's going to take place takes place in one single chain. So we should not get diffusion blur, and if we're lucky, we can get out of this triangle. So how does this work? The unzipping polymer, and I'll show you some more about it in a minute, is this strange polyester, the one that we like the best at any rate. And this, I'll show you more about this, but when you shine light on this polymer, it undergoes a cleavage that results in the depolymerization of the polymer to its back to nothing. And the product of this is carbon dioxide, this, and CO2. So shine light on it and it disappears when you shine light on it. It's very interesting and weird polymer. If you cast a film of this, you have a very sensitive patterning material, but the pattern you've produced has no value, because if you try to transfer the image into the substrate or use it for anything, it unzips. So it's a very sensitive imaging material, but it has no use in the manufacturing process. So what we did was to borrow from the old resist design because it has such poor etch resistance. And remember that traditional eye-line resist had diazonaphthoquinone. This is the etch-resistant matrix resin, and this is the substance that changed the inhibitor that could be changed to a promoter. And we just switch this and use this as the analog of the diazoquinone in the design of the resist. Mix this stuff with the Novolac, slow down its dissolution, shine light on it, and the products do not inhibit dissolution. One is a solvent and the other is a gas. So it doesn't inhibit the dissolution. And the resin has excellent etch resistance. So this is the design. Okay? So here you see the same cartoon. Here's the Novolac resin. We add the unzipped polymer, slow it down, shine light on it. It goes to monomer. The monomer doesn't inhibit dissolution, and we can do it just like this, hopefully. So we just need an unzipping polymer. So I hooked up with, I went to Penn State, and I was walking around talking to faculty, which is sort of the way the process works. It's always great fun. I had a wonderful time today. And one of the people I met was a young man named Scott Phillips, who was, anyway, he was working on biological stuff, but I was impressed. And I thought, I wonder if I can entice this person over to the dark side to work on polymers without worrying about them being biological. And so I decided that I'd try that. And so we wrote a proposal together, got some money, and set out to try and test this theory that I sort of described. So we made a lot of unzipping polymers. I won't go through the whole list of them, but there are more than this. Several of them have been seen before. Some of them never had been seen before. Some of them unzip beautifully. Some of them, they all unzip. Some of them are too slow. But in order for this to work, they have to unzip efficiently in the solid state, which they don't all. They have to be inherently sensitive to radiation in the wavelength region that we're interested in. They have to be thermally stable to be able to be processed and to bake the films enough to drive off the solvent. And they have to be phase compatible with the matrix polymer, which I think many of your faculty can tell you is an uncommon characteristic. You mix two polymers together, generally they phase separate. So we're asking a lot of this stuff. Please find something that fits into this box. I was talking to the students about this before. We've got this properties box, and if you can find something that'll fit in the box, you win. But it has to fit in every one, it has to meet every one of these. The only one that met every one of them was this one. And it was made by Ryan Mesh and Kensuke. Long story that I won't take you all through, but it wasn't easy to make it. The idea was that we would put a photosensitive end cap on this polymer and then cleave this bond photochemically to generate the terminal anion. And the hope was that this terminal anion would depropagate to form CO2 and toluene. So classical photochemical blocking group is orthonitrobenzyl group. So we made the orthonitrobenzyl ester. And we cast films of that and films of the methyl ester as a control. And then we tried testing them. And this remarkable thing was that you couldn't tell one from the other, which is to say that this is not important. The polymer itself, some aspect of its structure is intrinsically radiation sensitive. Hip, hip, thank you. I'd like to say that we designed this based on application of density functional theory, quantum mechanical calculations, and computational analysis of, that would be a lie. It was by luck. So it was hard to make this monomer. We do a Birch reduction and alkylation. This reaction was hard to optimize, and a student came back and told me that he had found how to make it work properly. You need to add a little water. I'm going, excuse me? You added water to this lithium metal dissolved in liquid ammonia, and you didn't come to see me before you're going to be punished. And anyway, yeah, if you put a little bit of water, you have to use wet THF, or it doesn't really work very well. But if you do, wow, it's great. You can get this dyeing in high yield. We make this ester. We tested many esters, but you need an ester with relatively acidic ester to be a good leaving group, because this is made by a Carruthers-like step growth polymerization, and we need the leaving group to come off, and yet it needs to survive some other steps in the reaction. So this turned out to be the optimum leaving group. And then we learned how to do this oxidation, diallylic oxidation. It only works if you use sea light. because, of course, everybody puts sea light in their reactions, right? You put sea light in all your, yeah. And then we did this Loix reduction, which has this strange reagent in it. And I will just quickly tell you that this was the toughest one. There was an undergraduate that had worked through all of this. His name is Wade Wong. He's now at MIT. And he could make this in good yield and significant quantities. But he's leaving to go to MIT. So I had a postdoc who arrived, and I asked him, look, I want you to go and start from air, earth, fire, and water. Stand right next to Wade and make this stuff so that when he goes away, we can still have it in the lab. So they did it, and it all worked until he got to this step. Wade got 100% of this, and the postdoc got 100% of the methyl ester. So we had to go back and say, you know, okay, Wade, which shoe did you put on first when you got up, and so forth and so on, until we could find something they did differently. The different thing that they did was that the postdoc used methanol for the reaction from the solvent purification system. It goes through a zeolite type molecular sieve system. And Wade used it out of the HPLC pure bottle. And when they switched, they got the inverted result. So there's eluting from the column that is the world's most efficient transesterification catalyst that someone needs to identify. But for us, we just used the bottle. And so none of this is simple. At any rate, then it took a while to learn to make the polymer. And I'm not even going to go through this to make the polymer, except to tell you that that boy that was the new postdoc could make the polymer. And he wrote down very careful notes, and he left, and no one could make the polymer. And a year passed of people trying to make the polymer. Finally, and we had multiple Skype shtick and talking, and finally I flew him from Japan back to Austin, and he made the polymer again, right in front of everybody. And then he left, no one could make the polymer. It was a matter of purification, but ultimately we now can make the polymer either by classical sort of initiation with butyllithium or with thiourea-based systems. And we use this one because the purification is easier. There's nothing but butane being generated. And it makes a nice polymer. It contained always a low molecular weight impurity. And so the student who was making it then managed to isolate some of the impurity, and it turned out to be this cyclic tetramer. Turns out that there are two diastereomers of this alcohol, hydroxy acid, and the one that has the alcohol and the carboxylic acid group cis on the ring forms the tetramer. The other one cannot. So we learned to separate them one from the other, and if you use essentially largely this one, you get a nice polymer. This one gives a low molecular weight polymer, and the cis-rich fraction doesn't make a polymer at all. So here you see the example of shining light on the thing. This is the polymer before exposure to light. Very quickly it forms the toluene and disappears. It's a very clean reaction. It works very nicely. So what's going on here? How does it actually cleave? Why does it cleave without having the in-group business? So the hypothesis was that maybe it does homolysis of this bond, which is sort of like a Norrish type 1 photoreaction that's well known. And that would mean that we're dealing with free radical. What we did was to add a radical trap, a well-known radical trap, and run the thing in an NMR tube with deuterated benzene, and then you could find this product if the radical was formed by ESR spectroscopy. And sure enough, the product that was formed had a very interesting and complex spin characteristic. I don't do this kind of spectroscopy, so I was ready to just say, obviously we have a free radical intermediate, let's go on. But no, the student was better than I am, and he decided to look more closely. And he found that it's possible to actually find free simulators for ESR spectroscopy, and he simulated this structure, and good grief, it looks almost fake. So I think we have a fair level of confidence that it is a free radical reaction and that this intermediate is being generated, and this whole unzipping thing is going on from radical intermediates. So anyway, made a photoresist of the material. Here we're shining differing doses on it and seeing how much of the film is left after exposure. At low doses, it doesn't dissolve at all. At high doses, it all dissolves away. This is polymethyl methacrylate, which is sort of like a standard resist for this kind of exposure. And this is the new stuff. It's obviously a lot more sensitive than PMMA. And it makes nice patterns. And if you change the molecular weight of the polymer, as you increase the molecular weight, its sensitivity increases, which is consistent with what you would expect if it's behaving or functioning the way we say. And the difference in the fast and the slow one, if I do ocular line edge roughness analysis, they're not horribly different, but the sensitivity is significantly different. So that's a good sign. Then we tested some other resins, and we discovered that this resin, which is also a base-soluble resin, it's available from this company. Wow, huge improvement in the amount of exposure dose required to pattern it. Very much lower dose gives the patterns. And so now I'm saying, is this rougher than this? If I gained in speed, I have to have suffered in line edge roughness. And it doesn't look that bad. At least it was encouraging. So we engaged, made a whole bunch of, put a whole bunch of resists together, and engaged this company whose job it is to measure line edge roughness quantitatively. And they measured a bunch of things that I didn't really fully understand, the correlation lengths and the power spectral distribution and so on. But the key thing is that what you want is to have a long correlation length, which means smooth sides, and a low dose. So the blue thing should be long and the red thing should be short. And so generally, if you shorten the red thing, according to the triangle of death, the blue thing should go with you. That is, you should suffer in line edge roughness. It's not that bad. I mean, looks encouraging. Do I dare write a paper saying I've escaped from the triangle? Not yet. But I'm not embarrassed to show you the result, I guess, is the status of the project at the moment. So we're continuing to do this, and we will continue to do it, and I hope that I'll be able to report that we're out of the triangle. I'm going to show you one last thing, and quickly, that in a very shallow way, that is another approach to improving the resolution of the system. A completely different one. We're going to try and break Lord Rayleigh's rule. Who is Lord Rayleigh? Lord Rayleigh is not named Rayleigh. His name is John William Strutt. I was surprised to learn that. He was the third Baron Rayleigh. He was born in 1842. He won the Nobel Prize in Physics in 1904. He did not win it for this, which is Rayleigh's rule. What he won it for was the discovery of argon. So why was that a physics prize? But anyway, sort of like, why are these microscopy awards chemistry prizes? But anyway, this is Rayleigh's constant. And according to the physics, which we could discuss if we had time, this cannot be smaller than 0.25. So first, to show you how this works, I have to explain something. If you take a mask made by the way I described, and you shine light through it, and you put a sensor downstream of it, you see that where it's transparent, all the light goes through. Where it's opaque, none goes through. And you get this delta functions that are on, off, on, off, on, off. This intensity function is then transmitted through this tremendously expensive tool, and this sharp image is blurred to junk. And the intensity function that was so beautiful is, for all practical purposes, destroyed. And now what happens is if you've paid these optics people to destroy your image, you have to somehow fix it back into a square wave relief image. And the way you do that is by some kind of amazing chemistry. So you hire a chemist and pay him a few cents to fix all of the problems created by the guy with the $90 million machine. the picture of life. So how do you take this sinusoidal thing, which I can explain where it comes from if we had the time, and convert it into the square wave image? See, all this is dissolved away, this is left behind, this is dissolved away, this is left behind, and so on. So conceptually, the way you do it is you have this sinusoidal image, and if you have a material which, when you expose it to light, the rate of dissolution increases linearly with dose, then all you do is convolve these two functions and you get a relief image that looks like that. It replicates the intensity function. If you can design one that has a situation where you shine light on it and nothing happens, and nothing happens, and nothing happens, and then suddenly it becomes soluble. And if you can position this suddenly it becomes soluble point right here on the intensity function, then you'll get this. Because it's insoluble, 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 suddenly it becomes soluble. So it becomes soluble for all doses above this to here, all doses above this to here, and so on. Clear? Okay. So just to show you that that's a cartoon, these are real data. Here's a modern resist. Shine light on it, nothing happens, nothing happens, nothing happens, nothing happens. And then suddenly, over a distance of only a couple of millijoules per centimeter squared, it switches 5 orders of magnitude in dissolution rate. That's a remarkable thing to have happen. And it took quite a while for people to learn how to make that happen. Anyway, this switching point, everybody calls E0. I don't know why. You could call it anything you want. Okay, hang on, here we go. Right now what's happening is we position the E0 right here on the intensity function. This mask is going through the lens, it's blurring the image, and this is the intensity function. And it's, for all doses above this, it's soluble, so you develop the line. It becomes insoluble again when it goes below, then it becomes soluble again, and you produce this relief replica of this pattern. It's okay? So what if we could do this? We move the threshold down so that the dissolved area is way too big. And then we install, conceptually, a new threshold here, above which the material becomes insoluble. Now what will happen is it's insoluble here because it hasn't had enough light. It's soluble between here and here because it's above the E0. But now it's crossing the EN, the negative thing. And for all doses up here, it's insoluble, so you print another image spontaneously or automatically between the two. And now what's happened, if I could make that happen, we would, and I wouldn't be telling you about it if we hadn't obviously figured, is you would have twice the frequency here as you do here, double the resolution of the lens with chemistry. I think that would be exceptionally cool. So we set out to try and do it. I won't go through all the things that didn't work, but in the end, what we decided was the approach should be that the thing that we're really looking at is acid concentration. You have to get enough acid to reach this E0 point. So if you had a substance, when you shine light on it, here's acid, here's dose. The acid increases as it should, like a first order reaction. And then it crosses the E0 point. And so for all doses above this, it's soluble. So here's the film. This dose is not soluble. Here it's soluble. And then somehow it has to go back down across this film, this E0, and become insoluble again. And if we could do that, you'd see we'd get this result, because it's soluble here, insoluble, soluble. So how do you, I need to somehow have photochemistry destroy the acid at higher doses. That's the challenge. How do you destroy acid? Oh! She invented it. Base. Exactly. That was really an advanced concept, right? So what we do is we have this photoacid generator, that salt that I showed you that's in the system. Shine light on it, it makes acid. And it has a kind of first order dose response that I can plot like this. When you use up all the photoacid generator, further exposure does nothing. Then we mix in with it, before we do the exposure, a photobase generator, which produces base. And the base that's produced kills the acid to form salt, which has not a useful catalyst. And if, and only if, you can arrange things such that the rate of the base generation, which is this blue line, the slope of this blue line, is faster than the rate of the acid generation, which is this other line, which I can't tell the color of. And if the total amount of base you can generate, which is here, is more than the acid that you can generate, then something fascinating happens. If you look at this little section right here, that place has net acid, and nowhere else in this plot is there acid. So here the base is being generated. Now it's stoichiometrically equal to the acid, and now above this there's excess base. So and if I lay that down, whoa, it looks almost like that cartoon. So when we saw this, we're going, okay, yeah, let's do this. But let's do this means please make a photobase generator that has kinetics that you know. I don't know how to do that. So not knowing how to do it, I asked this young man to make this, which is, we had made this in previous life, some work I did with Rashid many years ago. And it's a way, we're certainly not the inventors of this, but you can cleave this thing, this carbamate, it loses CO2, and there's a disproportionation reaction that produces an amine, which is the base, and a nitrosoaldehyde as the other product. And you can watch the rate of this by disappearance of the nitro group in the IR. But I don't know what the rate of the acid is, so it's not helping me. But anyway, I said, oh, it's so cool that if it were to work, just go make it and let's see what happens. So the kid comes back. He mixes, this is sort of a generic resin for this kind of a thing. It's not a T-butyl carbonate like I showed you, but it's the same chemistry. These are tertiary esters that cleave. And here's the salt. It's not the antimonate, it's the nonaflate, but it doesn't matter. And he decided to make the cyclohexyl derivatives because it's less volatile. And he mixed it up in brew, and he brought back this plot. And I'm going, woo, the likelihood of that is like less than winning the lotto. Because in order for this to do this, you have to have exactly the right matched kinetics. Where did the exactly right matched kinetics come from? This is where you'd like to say again, you know, quantum mechanical blah blah. No, it came from God, luck. Pure, unadulterated, freaking luck. Nothing else. Thank you. It was so perfect, you know, very steep on this. I look like a cartoon that I didn't question Shinyu's when he told me that these were his data, but I was so excited that I really needed to see if I could do it myself. And I did, and it did, and wow, I thought this is amazing. So this, yeah, that was luck. And this, we were being paid by this company to do this, and we had continuous, they were, how does one say, very interested in the work, and they were asking quite often how we were doing. And so they had seen the result, and they had, they were down in the lab before we were even sure we could make this stuff again, and took Shinyu up to Portland and printed the thing with the 440 nanometer pitch image and printed a 220 nanometer pitch pattern. And that, if you put all the numbers in and calculate the thing, that's a K factor of 0.15, which is below the Rayleigh limit. So we're, hallelujah, we broke that guy's rule. Here's, if you look, you know, when this first happened, this happens very infrequently in your research career. I've had more than my share of such good luck events, but you know, I can't hear what my wife is saying to me. I can't remember if I ate dinner. I can't function except to think about, God, let's go try this, let's try that. And so it's a really intense and wonderful rush or excitement that's very rare. And so anyway, once I calmed down from this, and I started looking at it, I'm going, what, this is ugly. This is okay, this is ugly. This is ugly. It's not good enough to pattern, so we need to fix that. So we set out to fix it. I don't have the time to tell you the details of how we fixed it, but we did fix it almost completely. And it's thanks to Ryan Mesh and Shinyu Gu and Wade Wong, an incredibly talented undergraduate. And I'm very much indebted to them. This paper it's sitting on my desk, it's still not published, and I have to get it out of there. But I'll tell you that I wish I had more time, because tomorrow I'm going to show you another one of these projects. Well, at least at the lab, I'm going to show this project in which we actually managed to make 50 angstrom wide lines and spaces, and to transfer those images into underlying substrate. This is a cartoon of an influenza virus of the kind I showed you before. It's 100 nanometers in diameter. If you put that little sucker up on top of the pattern, you can see how small, they're the size of the internal parts of viruses. And I hope it's making this guy happy. This is Gordon Moore, the guy who wrote the law. I'm hoping it's making him happy, and I'm looking forward to telling that story tomorrow. I want to thank all these people who helped us. They gave us money to help keep the students warm and fed. And my main job was just to herd them into the laboratory, make sure they didn't hurt themselves or do anything stupid, and they did it all largely by themselves, as they always do. So I thank them and all these people these are all undergraduates, these are graduate students, these are people who helped me feed all these people, and I thank you for listening to the story and for inviting me.
We can warm up with graduate student questions before moving to like the clinical question that you texted Austin along with that. So who would like to start? Okay, then I will. I'll ask the basic. So in this last bit, Grant, where you see the alternating line edge roughness between the two.
Yes.
Is that due to reaction diffusion kinetics of the two species, the acid and the base?
That's not the critical factor. The critical factor is that, can I write on that?
I don't mind if you write on that. Now this harder question is,
So the critical factor is that if you look at the plot of concentration of acid as a function of dose for the Photoresist acid generator, remember it looked like this, right? And then there's this plot of the base here. So if you look at the net slope of the formation of acid here, you have to subtract from this slope the slope of the base. And that means that the actual, when you look at this plot on the side that we showed, look like this. This is very sloped, and this is actually even more sloped. And the fact that it's so gradual means that the definition of where the edge is not crisply defined. It has low contrast, so to speak. So in order to make those rough edges go away, what we needed to do was to steepen this up. And the way we steepened it up was to, instead of having this kind of base kinetics, we needed to have this kind of base kinetics, so that in this region, this is not subtracting from the slope of the acid generation. And we did that by designing systems that have a something we call a latent photo-based generator. So you have a latent photo-based generator which reacts with light to form a photo-base generator which reacts with light to form base. So at the beginning, you're making this. And then once the concentration of this reaches enough, you begin to go up. And learning how to do this and to match the quantum efficiency of these two reactions and so forth was quite a challenge. But they did it and showed that even though it's not a perfect solution, that the principle is correct. And so we always hope that, or think, I guess, that our job is to show how to do it in principle, but not to try and optimize it or produce a product, so that hopefully some resist company or somebody who sells product of this sort will pick up the ball and optimize the thing and make one far better than the ones we made. At least we know what to make. It's just the details need to be sorted out.
Thank you. All right, other questions? Silicon has been the material
They're cheating you. They're cheating you. So what happened in the olden days, you had the 40 nanometer generation, and then you had the 32 nanometer generation and the 28 nanometer generation and so forth. What they're talking about was the minimum feature was that many nanometers wide. Well, they continue this nomenclature, but they don't continue the relationship between the smallest structure and the name. They could just as well call the generations alpha, beta, gamma, or Sally, John, Peter, whatever, because they have no relationship to the size of the structures that they're building. Anyway, yeah, so they're saying 7 nanometer thing, but it's 14 nanometer is the minimum dimension on the product.
So my question is, can you comment on post-silicon?
Post-silicon. That's retirement. No. Post-silicon, I don't think post-silicon is going to be an important thing during the next many years. There's new classes of devices like quantum computing devices and so forth that they are also built on single crystal silicon. That stuff is here to stay. The infrastructure for building it, producing it, handling it, printing it, and so forth is so well developed that it'd be very difficult to argue to get rid of it. But what will happen, I think, as I was telling the students that we met earlier today, is that this process that went on during my career of continuously trying to reduce the XY dimensions, the planar dimensions area of a transistor, to get more of them on a chip. There are two ways to do it. One is to continuously make them smaller and hold the chip size constant. The other is to leave them the same size and start stacking them up on one on top of the other. And that's where the things are going. They're going to get more transistors on a chip, but I think they're going to get them there by stacking them one on top of another. The city of Austin discovered fairly recently in the last 10 years, they were, they charge property tax on the unit, on the amount of area of your house. So they have a place that's, 100 meters by 100, or 20 meters by 20 meters, and they can collect X taxes. But if you stack a 50-story condo on top of that, you can get 50 times that much tax from the same area of land. So they're doing the same thing. We'll put they love this new discovery. I hope it doesn't hit Knoxville. And so I think that they're going to do is to create skyscrapers on top of the thing. The challenge is to find ways to remove heat from these devices because they're generating enormous amounts of heat. And that's partly can be improved by redesigning of the devices, and partly by devising materials that are capable of transporting the heat away from the devices themselves. So I think that's going to be a great fun project, really fun project for some people in the future.
Chris, please. So later projects was specifically talking about getting rid of the catalyst, yet the other one was adding catalyst and base to arrange both. Do you think that one of them has more of a, like a...
In terms of it being adopted for end use? The first one is more likely than the second because it's a complicated story. But right now there's a lot of pressure behind a particular solution using long wavelength X-ray radiation, so-called EUV, extreme ultraviolet radiation. And that printing technique requires these chemically amplified or catalyzed resists, and it's causing them serious problems. And so if we could help the EUV program by getting rid of this diffusion-based bias, it would have a huge impact. So I think that one is more likely to be important than the second one. But the last one is probably more likely than the other two, the thing with the very small structures. You're coming to Austin, right?
Other question, Jordan?
When you're going from the images of 200 nanometers to 100 nanometers, are you changing the width of your mask, or are you changing the chemistry?
Okay, in the case of the system that I showed you, doubling the pitch of the thing, the mask stays the same. So if you, I mean, it's fun to show this to the non-chemistry people because you can take a bottle of photoresist and a mask and you print it and it'll print 200 nanometer lines and spaces. Then you pour some of the stuff into another jar, sprinkle some white powder in there, squirt it around and print again, and suddenly it prints. Don't change anything else, just sprinkle this magic dust into the photoresist and it doubles the resolution of the lens. And they're like, ooh, let me give you money. Okay. It's really makes me feel good to see chemistry improve the physics. It's not improving the physics, it's just making smaller structures. But if you wanted to change the exposure system in some way that would double the resolution, it would cost quadrillions of dollars. And this is just, spoon some white powder in the jar. So I'm hoping, we'll see. My children need shoes, so.
Any other questions? The groundbreaking pieces for the new first Texas at Austin? Try to save those for our side. Okay, please join me in thanking Professor Willson.
Thank you.